Tonight, drift toward Mu Cephei, a deep garnet supergiant glowing near the edge of the Milky Way. Its light carries a quiet story of layered atmospheres, drifting dust and slow winds that fade into the galaxy's dark lanes. In this cosmic sleep documentary, the journey moves gently from a red limb of starlight to faint shell's filaments, and the soft blur where a star's halo becomes shared space. If this calm science voyage helps, please like the video, subscribe for more long sleep documentaries, and turn on notifications so the next night sky story is ready when needed. A deep red point of light hangs near the Milky Way's outer lanes. It holds steady and dense like a coal that refuses to cool. Mu Cephei appears garnet red because cool starlight and a wide hazy atmosphere tint what escapes. In that region, darkness is not empty. Dust lanes form soft rivers through crowded stars. Against that layered backdrop, one ember-coloured source seems to stain the nearby black with faint rose. The first unlock is simple and calm. Colour is not decoration here. Colour is physics made visible. Light leaves the star from a layer that behaves like a glowing skin. It is not a hard boundary. It is a depth where gas turns from blocking light to letting it pass. The edge fades instead of cutting off. A broad disk would appear if the star were close enough. The centre would look brighter than the rim. This is limb darkening. The centre view reaches deeper layers where gas is warmer. The rim view skims higher layers where gas is cooler. A real physical gradient crosses the disk. Brightness softens toward the edge. The colour also shifts a little toward deeper red. The visual anchor lingers on the rim. A rosy halo fades into space. The boundary looks like fog thinning in still air. The second unlock arrives in the same scene. The star looks red partly because its visible surface is cool for a star. Temperature guides the overall tone of the light. Hotter surfaces peak at bluer colours. Cooler surfaces peak at redder colours. Mu Cephei sits in the cool range for a luminous star. Its surface is about 3,500 Kelvin. That heat is close to fresh lava that still glows dull red at night. This single number carries a quiet weight. It suggests a swollen star with low surface gravity. It suggests an outer layer that expands and cools. Another visual anchor appears as a ribbon of light. The ribbon is smooth at first. Then it dips in places. Those dips lead to the next unlock. The star's light is not only shifted by temperature, it is filtered on the way out. A key term helps and then steps aside. Opacity means how strongly matter blocks light. In a cool supergiant, some molecules can exist in the upper layers. These molecules absorb some colours more than others. The spectrum is carved into broad bands. One contributor is titanium oxide. It darkens parts of visible light and leaves the red side less affected. The effect resembles late sunlight passing through thick haze. Shorter colours are reduced more strongly. The remaining light looks warmer and deeper. A third visual anchor holds the idea in place. A thin mist floats above the glowing disk. Light rises through it in long slanted paths. Some colours fade faster than others. The third unlock becomes clear. The garnet tone is created by cool emission and selective absorption together. One more scale shift arrives here. A single molecule can remove a narrow slice of colour. A whole galactic dust lane can soften an entire spectrum. Both effects push light toward red, yet they leave different fingerprints. Molecular bands create patterned dimming across the ribbon of light. Dust creates a smoother tilt like a thin fog spread across many colours at once. A sixth visual anchor makes the difference tangible. The ribbon lies against darkness. In one case it shows distinct shadows, in the other it fades evenly from blue to red. At this distance, what is seen depends on what lies between the star and open space. Interstellar dust can dim light. Interstellar dust can also redden it by scattering shorter wavelengths more strongly. This creates a limit of observation that stays precise and gentle. The true brightness and the true size depend on distance. Distance is uncertain for far objects. A small error in distance becomes a large error in inferred radius. Another limit follows close behind. The star's edge is not sharp. Its apparent size depends on where the fading limb is defined. When the halo is thick, the definition shifts. A small shift changes the estimate of the disk. The fourth visual anchor is a slow inference. The star's disk is traced by a faint contour. The contour moves outward or inward as the haze brightens or thins. The fourth unlock is about humility. Some facts are known in broad strokes. Some remain ranges shaped by soft boundaries. The star's vastness can be suggested without crowding the mind with more numbers. Its outer layers extend far beyond the scale of ordinary stars like the Sun. Gravity at the surface is gentle compared to the star's interior pull. Gas can lift and drift through the atmosphere. The atmosphere can swell into a broad halo. Light does not leave from a flat plane. Light leaves through curved layers and through moving pockets of density. The motion is slow and rolling. It is a shifting patchwork of slightly different temperatures. A fifth visual anchor settles into view. Bright cells appear and fade across the surface like warm eddies on a calm sea. The pattern changes without hurry. The changes add texture to the colour. The fifth unlock is quiet and immediate. Even a simple red point can hold structure when the scale is allowed to expand. The Milky Way around Mu Cephei remains a field of calm context. Pale points cluster along the galactic band. Dark lanes divide them into shapes like smoke in still air. The Garnet Star remains distinct within that tapestry. Its redness marks a cool surface. Its softened rim hints at an extended atmosphere. Its filtered light suggests molecules that survive in those outer layers. These clues settle together without urgency. The section ends where it begins with the ember in the dark. In that region, light behaves as both messenger and sculptor. It carries information, and it is shaped by the medium it crosses. The next step is gentle and grounded. Section 2 follows the same logic and turns colour into a quiet measure across stars. Colour arrives as a quiet code carried by starlight. It points back to temperature, but only after the light is understood as a broad spread rather than a single tone. A star's glow begins as thermal radiation shaped mainly by heat in the emitting layer. Imagine a long, calm shoreline of colour. The blue end thins into darkness on one side. The red end thins into darkness on the other. Between them, a gentle rise and fall forms a smooth hill. That hill is not drawn in ink. It is built from countless photons leaving hot gas. The first unlock is steady. The overall curve reveals the surface temperature more reliably than any single hue. A clear physical detail sits inside that curve. The brightest part is not at the extremes. It sits near a peak. On either side, intensity slopes down like a long dune. In that region, light behaves as a thermometer that is made of colour. A second visual anchor settles in. A faint ribbon of light stretches through space. It is not cut into sharp bands. It's a continuous glow with a rounded crest. The crest moves when temperature changes. The crest moves toward shorter wavelengths when the surface is hotter. It moves toward longer wavelengths when the surface is cooler. A single number can hold the scale without strain. For a surface around 3500 Kelvin, the peak tends to fall near about 800 nanometers. That wavelength is like the deep end of visible red, where colour becomes hard to separate from near infrared. The second unlock arrives at once. A cool supergiant can look red even while it radiates far more energy than smaller, hotter stars. The size and the temperature divide the work. The temperature chooses the colour balance. The size sets the total output. Another visual anchor appears as a soft gradient across a wide disk. The centre gleams warmer. The rim looks darker and redder. The gradient is real. It comes from different depths along different lines of sight. The term blackbody can help if it is kept simple. Blackbody means ideal surface that emits light based only on temperature. Real stars are not perfect blackbodies. Their gas layers absorb and re-emit in selective ways. Still, the blackbody curve gives a calm starting point. It gives a baseline hill shape. The third unlock is gentle. Once the baseline hill is known, deviations become clues about the atmosphere. A new physical detail enters without sharpness. Broad dimming can appear in certain colour ranges. It can look like shallow valleys carved into the hill. In cool stars, molecules can survive in upper layers. Those molecules absorb many nearby wavelengths at once. The curve is not broken into thin notches, it is pressed down into wide dips. The dips deepen the red appearance by removing some of the shorter colour contribution. A fourth visual anchor holds the idea in place. The glowing hill of light looks as if a soft hand presses it down in a few broad places. The crest remains, but the left side sags more. The red side remains comparatively higher. The fourth unlock becomes clear. Redness can come from cool emission and from filtering in the outer layers. These two causes can mimic each other if only a single colour is measured. Here, the limit of observation enters specific and calm. Temperature is not measured directly from the surface. It is inferred from the light that escapes. That inference depends on how dust and gas reshape the spectrum. Interstellar dust tends to scatter shorter wavelengths more. It can tilt the curve without adding sharp dips. Molecular absorption tends to create wide valleys. When observations are sparse, the two effects can blend together in the estimate. Another limit follows from geometry. A red supergiant has an atmosphere that is extended and uneven. Different parts can contribute at different depths. The measured colour can shift as the atmosphere changes. That shift can happen without any dramatic event. It can happen as slow patterns move across the disk. The fifth visual anchor returns to the limb. A faint halo surrounds the star. The halo is thicker in some directions. The boundary looks more like layered smoke than a crisp edge. At this distance, a signal would average over that complexity. It would mix light from different patches. It would smooth away fine structure. The fifth unlock is quiet and useful. A single colour index is never the whole story for a star like Mu Cephei. The spectrum carries more truth than any pair of filters. Another scale shift arrives from microscopic to galactic. A molecule in the outer atmosphere absorbs a photon in an instant. That instant leaves a statistical shadow across the spectrum. Over thousands of years, the star's mass loss can seed dust into the surrounding region. That dust can reshape light across vast distances. Both effects are small at the level of a single interaction. Both become large when repeated across long paths. A sixth visual anchor forms in open space. A wide lane of the Milky Way cuts across the scene. The lane is dark and soft-edged. Stars behind it appear dimmer and warmer in tone. The lane looks like a translucent curtain with thickness and grain. The sixth unlock settles in without effort. The galaxy itself becomes part of the colour measurement. It is not only the star that sets the hue, it is also the path the light takes. This does not erase what colour can tell, it simply adds conditions. Colour still points towards temperature. It still suggests the cool surface of a red supergiant. It still hints at molecular absorption in the upper layers. It still pairs naturally with the idea of an extended atmosphere. The section ends by holding the curve as a guiding shape. A smooth hill of light rises and falls. The crest sits near long wavelengths for Mu Cephei. The hill is pressed and tilted by gas and dust. The next step remains close and tangible. Section 3 moves from colour to surface texture. It follows the slow rise and sink of hot gas across a swollen stellar skin. The red surface is not still, even when the star seems steady from afar. The mottled texture comes from slow convection that lifts heat and lets it sink again. In that region, light behaves as a tracer of motion. Brighter patches mark warmer gas that rises. Darker patches mark cooler gas that settles. The first unlock is immediate and quiet. A red supergiant does not shine from a smooth shell. It shines from a moving pattern of cells. The primary visual anchor holds close to the surface. A broad disk fills the scene with dim ember light. Across it, soft islands of brightness drift and blur. The borders between islands are not sharp. They feather into one another with gentle gradients. The rim remains darker than the centre. The gradient stays in place while the islands change. The effect resembles cloud shadows sliding over a calm plain. It is not weather. It is gas in motion under gravity. A second visual anchor appears along the limb. The edge looks like a thick rosy mist. Through that mist, the bright islands fade faster. The star's outline becomes a soft boundary rather than a line. The second unlock sits inside that boundary. Convection reaches into layers that partly block light. As warm gas rises, it expands and cools. It also becomes more transparent. Light escapes from slightly deeper places in those regions. The bright patches are not only hotter, they can also be clearer windows. This links surface texture to the atmosphere without strain. A term can help and then step aside. Convection means heat carried by rising and sinking gas. The image is simple and natural. Warm parcels rise because they are less dense. Cool parcels sink because they are denser. The scale in a supergiant makes the same process feel unfamiliar. The third visual anchor leans into scale. A single bright cell stretches across a vast area of the disk. It is not a fine grain like sand. It is more like a slow continent of light. Its edges curl and dissolve over time. A fourth visual anchor follows the motion. A darker lane forms beside the bright cell. The lane widens, then thins. It looks like a faint seam in red velvet. The first payoff arrives with this seam. The surface pattern explains why the star's brightness can drift over time without any sudden event. A small change in the balance of bright and dark patches can tilt the total light. It can also shift the overall colour by a small amount. This shift is gentle and slow. It is the sum of many motions rather than one cause. The primary analogy settles in as a natural one. The surface behaves like a peat bog seen from above. Warm bubbles rise under the moss. Cool water returns through dark channels. The bubbles are not fast. They take their time. They reshape the patterns without breaking it. The analogy carries without adding humans or machines. A scale shift arrives inside the same scene. In a small star, a convective cell can be tiny compared to the disk. In a red supergiant, a cell can be enormous. The second payoff lands with one safe number. A full turnover of a giant cell can take about 1 year, like the slow return of seasons. This is not a strict clock. It is a quiet order of magnitude. It explains why the pattern evolves on long rhythms. It also explains why the star can seem steady over a single night. The fifth visual anchor shows that rhythm. The bright island does not race. It drifts and reshapes as if under thick fluid. Its centre brightens, then dims. Its boundary frays into smaller wisps. Nearby patches merge and separate. The disk never becomes uniform. The second unlock deepens without new numbers. The contrast between bright and dark patches is controlled by temperature differences and by how transparent the gas becomes. In a swollen star surface, gravity is gentle. Gas can rise farther before it cools and turns back. This makes the pattern larger. It also makes the bright and dark boundaries softer. A sixth visual anchor holds the softness. The bright islands have cores that glow. Around each core, a pale penumbra fades outward. Between islands, darker valleys sit like shallow basins. No sharp crack divides one region from another. The third payoff arrives in the valleys. Those darker lanes are not empty. They can be higher, cooler layers that block deeper light. They are the places where the surface becomes more like a veil. They can also be where molecules survive more easily. This links texture to the same filtering that shapes colour. The connection remains calm. Convection changes density and temperature. Density and temperature change which wavelengths escape. At this distance, a signal would average across the entire disk. Fine details would blur together. Yet the largest structures can still imprint slow variations in brightness. Here, the limit of observation is specific and gentle. Surface convection is inferred from small brightness changes and from subtle shifts in spectral lines. The disk is hard to resolve cleanly. The halo further softens the edge. Even when the disk is measured, different layers contribute at different wavelengths. This means a map of the surface is always partial. It is a reconstruction rather than a direct view. The seventh visual anchor turns that limit into imagery. A faint red lantern shape sits behind thin fog. Broad shadows move across it. The shadows are seen, but their exact edges are uncertain. The third unlock rests inside that uncertainty. The star's surface is best understood as a set of tendencies. Warm gas tends to rise and become more transparent. Cool gas tends to sink and become more opaque. Bright patches tend to mark deeper, clearer lines of sight. Dark lanes tend to mark higher, cooler layers. These tendencies explain the observed texture without demanding perfect detail. Another scale shift arrives from the short to the long. A photon leaves a warm patch in an instant. That photon carries a memory of local temperature. Over months, the patch reshapes. Over years, the whole pattern slowly reorganizes. Over longer spans, the star's outer layers continue to change as it evolves. The eighth visual anchor widens outward. The mottled disk sits inside a broader rosy atmosphere. Beyond it, the Milky Way's dark lanes remain as a quiet frame. The final payoff settles into place. Convection makes the star's surface feel alive without human traits. It is motion under physics. It is heat moving through gas. It is pattern without intention. The closing transition stays soft. Convection stirs the outer layers and sets the stage for slow breathing changes in size. Section 4 follows this path and describes pulsation as a gentle swell through the same extended atmosphere. A slow change in brightness can feel like a distant tide across a red star. The change comes from pulsation, where the outer layers expand and contract on long rhythms. In that region, light behaves as both clock and pressure gauge. The first unlock is calm and direct. A red supergiant can grow slightly larger, then slightly smaller without any sharp event. The primary visual anchor begins at the limb. The rim is a soft arc of rose light. The arc thickens, then thins. The halo brightens, then fades. The boundary never becomes a hard line. It remains a gradient where glowing gas gives way to transparent space. The second visual anchor stays on the disk itself. Bright regions drift from convection. Their pattern changes as before. Yet the entire disk also shifts in overall intensity. The shift is gentle. It is like the whole surface is lifted and lowered by a broad, slow wave. The second unlock arrives with a physical detail. Expansion cools the outer layers. Cooling changes which wavelengths escape most easily. Contraction warms the outer layers. Warming shifts the balance of the emitted light. The colour does not flip. It only leans slightly. The star remains red. The red deepens when the outer layers are cooler. The red softens when the outer layers are warmer. A third visual anchor holds a concrete image of the mechanism. A thin layer near the surface turns slightly more opaque, then slightly less opaque. The layer is not a shell of rock. It is gas that can block or release light depending on its state. A term can be used once and kept small. Ionization means atoms lose electrons in hot gas. In cool layers, some atoms keep electrons. In warmer layers, more electrons are free. This changes how the gas absorbs and emits light. The first payoff lands inside that change. Pulsation is not only motion, it is a feedback between pressure, temperature, and opacity. When a layer becomes more opaque, energy is held back, pressure builds. The layer is pushed outward. As it expands, it cools. It becomes less opaque. Energy leaks out more easily. Pressure falls. Gravity draws the layer inward again. The cycle can repeat without any guiding hand. The primary analogy stays natural and unique. The outer layers behave like a slow swell of a sea surface under steady wind. A broad rise passes, a broad fall follows. The water does not travel far. The surface height changes. The star's gas also shifts in place. The radius changes modestly, the light output changes modestly. Another visual anchor appears in the atmosphere above the disk. A faint veil surrounds the star. During expansion, the veil looks thicker. It spreads outward and grows more diffuse. During contraction, it draws inward and looks brighter near the limb. The second payoff is immediate. Pulsation can help shape the star's extended atmosphere. When the outer layers expand, they can lift material to larger radii. When they contract, some material falls back. Some remains aloft if it cools and becomes less tightly bound. This creates layering. It also creates uneven density. Those uneven layers can scatter light. They can also provide cooler pockets where molecules survive. The scene widens for a scale shift. The surface pattern is a local texture. Pulsation is a global motion. Convection rearranges bright patches across the disk. Pulsation changes the size of the whole emitting region. The third payoff follows this widening. The same star can show both kinds of variability at once. One effect adds small ripples, the other adds a broad swell beneath the ripples. A single number can hold the rhythm without strain. For Mu Cephei, a prominent cycle can be about 2 years, like the slow return of a familiar season. The exact timing can drift. The rhythm can wander. This makes the star feel less like a metronome and more like a natural oscillator. The next visual anchor turns the number into imagery. A faint light curve rises over many months. It rounds off at a gentle crest. It then descends over many months. The curve is not perfectly smooth. Small bumps sit on its flanks from convection. Yet the broad hill remains visible. The fourth payoff arrives on that hill. The long period implies a large low-density envelope. It implies that sound waves in the star travel slowly through extended gas. It implies that pressure changes take time to organize across the surface. The star's sheer size sets the pace. The concept remains restful because the timescales are long. The limit of intuition enters softly and clearly. It is hard to picture a star changing size because the change is not seen directly. At this distance, only integrated light is received. The radius is inferred from models and from how spectral features shift. Those shifts can be affected by moving layers and by uneven opacity. Brightness changes can also be influenced by dust and molecular absorption. This means pulsation amplitude so even period can be undone. The uncertainty is not a failure. It is a boundary set by distance and by a soft extended atmosphere. Another visual anchor makes the boundary tangible. The star is seen through layered haze in the galactic plane. The haze dims and reddens light. A small added veil near the star can mimic part of the pulsation signal. The fifth payoff becomes clear. A clean separation between true size change and atmospheric filtering is not always possible. Instead, both are treated together. Pulsation and atmosphere interact. The atmosphere responds to motion. The motion changes the atmosphere's transparency. A final scale shift stretches time outward. A single expansion and contraction takes years. Thousands of cycles pass over a few thousand years. Over longer spans, the star evolves and the envelope changes. The pulsation modes can shift as internal structure changes. The same basic feedback can persist while its details drift. The last visual anchor returns to the limb. The rosy edge brightens, then softens. The halo looks like stacked fog layers in a quiet valley. The layers do not hold still. They slide and thin, they thicken and drift. The closing payoff is gentle. Pulsation is a slow global heartbeat of pressure without any human trait. It is physics cycling through gas. It leaves a signature in light. It also helps build the star's soft extended boundary. The transition stays calm and forward. Section 5 follows the fading edge itself. It traces how a supergiant's atmosphere becomes a wide halo with no sharp border. The edge of Mu Cephei is a place where light fades rather than ends. That softness comes from an extended atmosphere where the last visible light escapes from a range of heights. A slow scene forms at the limb. The disk glows ember red. The rim darkens and then dissolves into a faint halo. The halo is not uniform. It looks like stacked sheets of rose haze. Each sheet is thinner than the one below. The first unlock sits in this boundary. A star does not have a single surface like stone. It has a depth where gas turns from opaque to transparent. The main concept is optical depth. Optical depth means how far light travels before it is blocked. When the optical depth is about one light can finally slip away. That single number is like one curtain layer in a shaded room. One layer dims the view but does not erase it. A second scene settles over the first. The halo brightens more along some arcs. It dims along others. This unevenness hints at clumps and waves in the outer gas. It also hints at a boundary that moves with time. The second unlock follows calmly. The apparent size depends on wavelength because different colours escape from different layers. Red light can come from slightly higher, cooler gas. Some near-infrared light can come from deeper, warmer gas. The star's radius is not a single value. It is a set of radii tied to different depths. A physical detail holds the idea steady. The limb is darker than the centre. This limb darkening is a gradient, not a stripe. The centre view looks deeper into the glowing layers. The rim view skims higher, cooler layers. The brightness falls because the line of sight becomes long and shallow. At that grazing angle, light passes through more gas before leaving. A third scene appears as a thin arc. The arc is the same rim seen from far away. It looks like a glowing crescent wrapped around the disk. The crescent is faint. It is persistent. The third unlock arrives in the crescent. A long path through gas increases the chance of absorption and scattering. Scattering means light changes direction after hitting particles. A clear image forms without strain. Light behaves as if it is nudged sideways by tiny grains and molecules. The nudges are small. The cumulative effect is not small. The halo becomes brighter in some directions because scattered light fills the edge. The halo becomes dimmer in others because absorption removes it. The primary analogy remains unique and natural. The boundary behaves like the upper edge of a storm anvil in twilight. The cloud top has no hard line. It thins into higher haze. Colour deepens where the path is longer. A fourth scene widens the scale. The star's disk is a bright island in a wider sea of dark. Around it, the halo extends far beyond the disk. The star is enormous in physical size. Its radius can be about 1 astronomical unit. That is comparable to the average distance between Earth and Sun. This single number is only an order of magnitude guide. It supports a calm shift in intuition. A surface that large has a weak grip at its edge. Gas can float higher for longer. The atmosphere can swell into a broad envelope. The fourth unlock settles in. A swollen atmosphere makes the boundary more sensitive to small changes in temperature and density. A slight cooling can allow molecules to form. A slight warming can break them apart. Each change alters opacity. Opacity returns as plain language. More opacity means light is trapped deeper. Less opacity means light escapes from deeper. The visible radius shifts with that trapping. The fifth scene returns to the limb in slow motion. The halo brightens for a time. It then softens. A faint band appears at a slightly larger radius. The band is not a solid ring, it is a gentle enhancement. It suggests a shell of gas that is denser than its surroundings. The fifth unlock follows. Pulsation and convection can lift material outward. Lifted material can cool and condense into a denser layer. That layer changes where light last scatters. It also changes how the limb looks. A scale shift carries the thought from small to vast. A single photon leaves a warm layer in an instant. Over months, the density in the halo can drift. Over years, shells can form and disperse. The visible edge responds as a moving contour. The limit of observation arrives softly and precisely. The star is far. The disk is hard to resolve sharply. Any measured diameter depends on where the edge is defined. The edge is a gradient. Different instruments respond to different wavelengths and different brightness thresholds. Models are used to infer where optical depth reaches the escape point. If the halo is clumpy, the inferred radius can change with time. This is not a mistake in nature. It is a limit set by distance resolution and a soft atmosphere. A sixth scene makes the limit tangible. The star appears as a bright core wrapped in a faint veil. The veil has slow ripples. The ripples blur together when seen as a single point of light. The measured size becomes an average. Fine structure is lost. Yet the softness remains as a signature. The sixth unlock becomes clear. The extended atmosphere is not a decorative fringe. It is a working layer that controls what is seen. It shapes colour through absorption. It shapes brightness through scattering. It shapes apparent size through wavelength-dependent escape. Another calm detail joins the picture. The halo has a temperature gradient. It cools outward. It also has a density gradient. It thins outward. These gradients make the boundary stable in form even while it shifts in detail. A final scene holds the gradients in place. The disk glows like a deep ember. Above it, the halo fades through rose to near black. The fade is smooth. The fade is layered. The last payoff arrives without urgency. A star like Mu Cephei is defined as much by its atmosphere as by its core. The edge is where internal physics meets surrounding space. It is where motion opacity and light negotiate an exit. The transition stays gentle and forward. Section 6 follows material that does not fall back. It traces how slow winds carry gas outward from this softened boundary. The halo does not stay close to the star forever. It thins into a steady outflow that carries gas outward as a slow wind. The first unlock is calm and direct. A red supergiant loses mass because its outer layers are loosely held and easily lifted. The primary visual anchor begins just above the softened rim. The disk glows deep red. A faint veil rises from the edge and stretches outward into a wide plume. The plume is not a jet. It is a broad drift with uneven density. Its inner part looks brighter. Its outer part looks like a thin blush against black. Physical detail holds the scene in place. The plume shows gentle striations. Faint bands arc outward like ripples frozen in smoke. Some bands are thicker. Some are almost invisible. Between them, darker gaps appear where the gas is thinner. The second unlock arrives in those bands. Mass loss is not a single stream. It can be lumpy. It can come in shells and clumps. Convection lifts material locally. Pulsation lifts material globally. Both can push gas to heights where gravity is weaker. Once there, radiation pressure can help. Radiation pressure is the push from light on a matter. A simple definition stays within a short breath. Radiation pressure means light transfers momentum when it is absorbed or scattered. The image is gentle. Light behaves as a steady breeze made of photons. The breeze is faint, but it acts for a long time. The third visual anchor forms around the star. The plume becomes a faint rounded envelope. The envelope is not uniform. It has brighter knots and darker hollows. The knots drift outward. Their edges blur as they expand. The first payoff lands inside this motion. A wind does not require violent ejections. A slow, persistent push can move gas beyond the star's loose outer grip. A single number can hold the pace without strain. The outflow speed can be about 20 kilometers per second, like a fast passenger train. That speed is small compared to light, yet it is enough. Over a year, gas moves far beyond the star's own radius. Over thousands of years, it can fill a vast region around the star. A scale shift arrives smoothly. A single atom responds in an instant to a photon's shove. A cloud responds over months as countless shoves accumulate. The fourth visual anchor turns the scale into imagery. The envelope looks like a slowly inflating lantern of reddish mist. Its inner edge stays brightest. Its outer edge fades into darkness. The second payoff becomes clear. The wind builds a circumstellar environment that later shapes what happens next. Gas and dust around the star become a record of past outflows. The record is written as density layers. It is written as arcs and shells. It is written as a symmetry. Some directions can carry more material than others. The next unlock rests on the cause of that asymmetry. Convection creates large surface patches with different temperatures and densities. Those patches can launch stronger local flows. Pulsation can add timing, creating partial shells. The wind then stretches those patterns outward. The fifth visual anchor focuses on a single clump. The clump moves outward while expanding. Its centre stays slightly denser. Its outer parts fray into wisps. The clump casts a subtle shadow in scattered light. Behind it, the envelope looks a touch dimmer. This shadow is a concrete physical detail. It reveals that the outflow is not a perfectly smooth fog. The third payoff arrives with the shadow. Clumpiness changes how light travels through the envelope. It changes where dust can form later. It changes how the star appears in different wavelengths. A limit of observation enters softly and precisely. The wind is hard to measure directly at great distance. Speed is inferred from broadened spectral lines and from models of the envelope. Those lines can be affected by turbulence and by overlapping layers. The wind can also vary with time. A single snapshot can miss long cycles. The inferred mass loss rate depends on assumptions about clump density. If clumps are denser, then assumed less total mass is needed to produce the same signal. This is a limit set by indirect inference and by unresolved structure. The sixth visual anchor makes that limit tangible. The envelope is seen as a faint glow around the star. The glow is smooth at first glance. A closer look reveals a grainy texture. The grains cannot be separated cleanly. They blend into a soft haze. At this distance, a signal would average over many clumps. The average hides extremes. The fourth payoff is calm. Even with uncertainty, the existence of a wind is robust. A red supergiant's low-gravity envelope and strong luminosity make outflow likely. The wind is a bridge between the star and the galaxy. It carries processed material outward. It also carries raw gas that can later cool and condense. Another scale shift widens the scene to the Milky Way. The star sits within a broader field of dust lanes and faint stars. The outflow adds a small local cloud to that larger texture. Over time, many such winds from many stars seed the interstellar medium. The cloud around Mu Cephei is one stitch in a much larger fabric. The final visual anchor returns to the plume close to the limb. The plume glows faintly in red light. Its bands drift outward without hurry. The closing payoff settles gently. The wind is the star's way of losing mass without drama. It is slow transport driven by weak binding and persistent light pressure. The transition stays soft and forward. Section 7 follows the drifting gas as it cools. It shows how dust grains can form and how that dust deepens the star's red appearance. The outflow cools as it drifts away and the darkness around it begins to gather texture. Dust forms when the gas becomes cool enough for tiny solids to grow, and that dust reshapes starlight into deeper reds. The primary visual anchor is a wide, faint shell around the star. It looks like a translucent blush that is brighter on one side. The inner star remains a dense ember. Around it, the shell shows soft arcs and patchy knots. Some arcs look like incomplete rings. Some knots look like dim beads suspended in space. The first unlock arrives inside that shell. Dust is not a smooth fog. It forms in pockets where density is higher and temperature is lower. Those pockets can come from clumps in the wind. They can also come from lifted shells that cool as they expand. A simple term helps once and then steps aside. Condensation means gas becomes solid grains as it cools. The picture stays plain. At first there are only molecules moving freely. Then a few stick together. A small seed forms. More atoms attach. The seed becomes a grain. The grain is tiny, yet it changes everything about the light that passes. A second visual anchor settles near the limb. The halo looks thicker along a particular arc. Along that arc, the star's edge seems softer and darker. The first payoff lands in that darkening. Dust does not need to block all light to matter. A thin veil can tilt the colour balance. Shorter wavelengths scatter more easily. The remaining light looks warmer and redder. Light behaves as if the blue end is rubbed away first. The red end persists longer along the path. The main physical detail is scattering. Scattering is light changing direction after meeting a particle. Some light is sent away from the line of sight. Some is redirected into it. The balance depends on grain size and wavelength. A single number can hold the scale without strain. Typical grains can be about 1/10 of a micrometer, like the finest sea haze reduced until it is invisible. This size is small compared to the wavelength of visible light, yet it is not negligible. It places the grains in a regime where colour dependence is strong. The second payoff arrives with this number. When grains are that small, blue light is scattered more than red light. This pushes the observed glow toward garnet tones. It also makes the shell visible as faint reflected light. A third visual anchor appears as a gentle fan of brightness. One side of the shell looks brighter, while the opposite side looks dimmer. This pattern is not a beam. It is a consequence of angle. Forward scattering sends more light in directions close to the original path. A shell seen at an angle can brighten where scattering angles favour the line of sight. The third payoff is immediate. The shell's uneven brightness can reveal the geometry of dust. A nearly spherical shell can still look lopsided because scattering is not equal in all directions. The scene remains calm as the view widens. The dust shell surrounds the star like a faint cloak. Farther out, the cloak thins and blends into the Milky Way's darker lanes. A scale shift arrives here. A grain grows over hours or days within a clump. The shell expands over years as the wind carries it outward. Over thousands of years, many shells can overlap. The surroundings become a layered record of repeated cooling and drifting. The fourth visual anchor lingers on layering. Multiple arcs appear at different radii. Each arc is softer than the one inside it. The arcs are not complete circles. They break where density is lower. They fade where the grains are fewer. The fourth payoff settles in those breaks. The outflow is not steady in detail. Pulsation and convection create times of stronger lift and times of weaker lift. Each episode can create a partial shell. Dust forms more readily in the denser parts. The result is a set of incomplete rings that mark past rhythms without any sharp boundary. The second core concept joins gently. Dust also absorbs light, not only scatters it. Absorption turns some light into heat in the grain. The grain then re-radiates at longer wavelengths. The energy is conserved, yet the form changes. Visible light becomes infrared glow. This helps explain a quiet paradox. A star can appear dimmer in visible light while still losing the same total energy outward. The fifth visual anchor follows this re-radiation. The shell looks faint in visible red, yet it would glow more strongly at longer wavelengths. The visible scene remains subdued, as if much of the brightness has slipped into a darker colour range. The fifth payoff arrives without new numbers. Dust can make the star look redder and dimmer at the same time. It can also make the star's edge look larger. Scattered light can extend the apparent halo. Absorption can hide the deeper layers that define the sharper disk. The visible boundary shifts outward into the dustier region. This links dust to the earlier idea of wavelength-dependent radius. The limit of observation enters softly and clearly. Dust complicates inference because it changes both brightness and colour. Distance estimates and radius estimates often rely on measured flux. If dust absorbs some light, the star can seem less luminous than it truly is. If dust adds scattered light to the halo, the star can seem larger than the core disk. Many measurements then depend on models of dust composition and grain size. Those models are constrained by limited spectral information. Clumpiness adds another uncertainty. A thin clump can mimic a thicker, smooth veil when averaged. This is a limit set by indirect inference and unresolved structure. The sixth visual anchor makes that limit tangible. The shell looks smooth from afar. Up close it has grainy knots and faint voids. The knots cast subtle shadows in scattered light. Behind them the shell looks dimmer. The shadows do not have sharp edges. They blur because the medium itself is soft. The sixth payoff settles in the blurred shadows. Even without perfect detail, dust is a powerful explanation for the star's deep redness. It provides a physical filter that acts outside the star. It also provides a visible structure that traces mass loss. The story remains calm and coherent. Gas leaves the softened boundary. The gas cools as it expands. In denser pockets, solids can grow. The resulting dust reshapes starlight through scattering and absorption. The closing transition stays gentle and forward. Section 8 follows the consequences of this veil for measurement. It explores why brightness and size estimates can shift when distance and dust share the same signature. Distance looks like an empty word until it starts bending every estimate of a star. The uncertainty in Mu Cephei's size and brightness comes from how distance and dust entangle the same signals. The primary visual anchor is a set of faint concentric circles around the star. They are not real rings. They are imagined surfaces of equal distance fading into the Milky Way's dark lanes. The star sits at the centre as a red ember. Around it a dust shell adds a pale blush. Behind it the galactic background adds deeper shadows. The first unlock arrives at once. Brightness at the observer falls with distance. If the distance is wrong, the inferred luminosity is wrong. A star that is twice as far appears 4 times dimmer. A single number can hold the idea without strain. A distance estimate might be around 6,000 light-years, like a path that would take 6 millennia at light speed. This number is a safe order of magnitude. It places the star far out in the galactic disk. It also places it in a region where dust is common. The second unlock follows from this placement. Dust makes the star dimmer and redder. Distance makes the star dimmer without changing its intrinsic colour. Yet when only limited light is measured, both effects can mimic each other. The first payoff lands inside this mimicry. Correcting for dust can brighten the inferred star. Correcting for distance can brighten it as well. If both corrections are uncertain, the luminosity can swing widely. A second visual anchor settles on a simple physical detail. The dust lane is not uniform. It has filament edges and soft cores. Stars behind it appear muted. Their colours shift warmer. The lane behaves like layered gauze across the scene. A third visual anchor moves closer to Mu Cephei. The circumstellar dust shell shows arcs and knots. It adds another layer of gauze near the star. The third unlock becomes clear. There are 2 dust screens. One is interstellar along the line of sight. One is circumstellar around the star. Both tilt the spectrum. Both can hide true brightness. A single measurement at one colour cannot separate them. Even several colours can struggle if dust grain properties vary. Here a term can help and step aside. Extinction means light is removed by absorption and scattering along the path. The definition stays brief. Extinction means dust reduces and reddens light passing through it. The image remains restful. Light behaves as if it is filtered through tinted glass that is not perfectly uniform. Some rays are dimmed more than others. The second payoff arrives with this tint. A red supergiant can look even redder than its surface temperature alone would suggest. Yet the extra redness does not come from the star's surface, it comes from the path. This matters because temperature estimates can be biased. If dust reddening is overcorrected, the star can be inferred hotter than it is. If dust reddening is undercorrected, it can be inferred cooler than it is. The next visual anchor holds a physical gradient. The star's disk shows limb darkening. The centre is brighter, the rim is darker. A faint halo surrounds the rim. That halo can be partly scattered light. It can be partly emission from higher layers. It can also include light scattered by nearby dust. The third payoff lands in the halo. Apparent size can be inflated if the halo is counted as part of the disk. A diameter can be defined at a brightness threshold. A softer threshold includes more halo. A stricter threshold includes less halo. Since the edges are gradient, there is no single correct line. The measurement becomes a convention supported by models. A scale shift arrives smoothly. On the scale of a dust grain scattering is an individual event. On the scale of 6,000 light-years scattering becomes a cumulative bias. A photon can be scattered once and still arrive. It can be scattered many times and arrive late in a different direction, or not arrive at all. The fourth payoff arrives with this widening. The observed light is not a simple beam. It is the end result of a long journey through structured space. The limit of observation enters softly and precisely. Distance for far stars is often inferred from parallax or from associations with nearby regions. Parallax becomes tiny at great distance. The angle is small enough that measurement noise and systematics matter. If the star's apparent position shifts due to its bright halo, the parallax can be biased. If the star is variable, the centroid can move with changing surface patterns. This is a limit set by resolution and by a non-point-like source. Another limit follows. If a distance is inferred through brightness comparisons, dust must be corrected first. That correction depends on the dust law. Dust law is the relation between reddening and dimming. It can vary with grain size distribution. If the dust law is wrong, the distance is wrong. The fifth visual anchor makes the limit tangible. A faint trail of light is imagined leaving the star. Along the trail, pockets of dust appear as translucent clouds. Some clouds are thin, some are thick. The trail bends and diffuses as scattering redirects photons. The eye cannot see the original straight line anymore. The fifth payoff lands with this loss of straightness. Uncertainty is not only about instruments, it is about the medium between source and observer. The star is embedded in a complex galactic environment. Its own outflow adds additional complexity. Yet the uncertainty does not erase what is known. The star is luminous. It is cool on its surface. It has an extended atmosphere. It loses mass. These broad truths remain stable across reasonable distance ranges. The final visual anchor returns to the imagined distance circles. The circles fade into the dark lanes. The star remains at the centre as a steady red ember. The closing payoff is gentle. Measurement becomes an art of separating path effects from source properties. The next step stays calm and deeper. Section 9 turns inward beyond the surface. It describes the layered burning inside the star and how the core builds heavier elements in quiet stages. Beneath the red haze, the star's interior is arranged in quiet layers. Those layers form because different kinds of fusion prefer different temperatures, building a nested structure over time. The primary visual anchor is an imagined cross-section that stays soft and muted. A small bright centre sits at the core. Around it, several thicker shells glow at different intensities. Each shell has a blurred boundary. The boundaries are not walls, they are gradients where composition and temperature change. The first unlock is immediate. A massive star does not burn all fuels in one place at one time. It shifts to new fuels as the core changes. A simple term helps once and then steps aside. Fusion means nuclei join and release energy. The definition remains short. Fusion means light nuclei combine into heavier ones and release energy. The scene remains calm. In earlier life, the core fuses hydrogen into helium. Later, when hydrogen in the core is depleted, the center contracts. Contraction raises temperature. A new stage begins. Helium fusion starts in the core. The next unlock follows without hurry. Each new fuel ignites at a higher temperature. This creates a layered arrangement. The deepest layer runs the hottest reactions. Above it, cooler shells run earlier reactions. A physical detail anchors the idea. The shells are not equal thickness. The inner ones are narrower, the outer ones are broader. The inner boundary of each shell is sharper in effect. Their temperature rises quickly with depth. The outer boundary is softer. Their heat and composition blend into the next region. The first payoff arrives as a simple logic. When a new fuel ignites in the center, the previous fuel does not vanish. It continues in a shell. This preserves energy output while the core moves on. The primary analogy stays unique and natural. The interior behaves like a set of nested river deltas. Each delta deposits a different sediment layer. New layers form at the center while older layers shift outward. The layers remain distinct, yet their edges blur where currents mix. The second visual anchor returns to the shells. The helium-burning layer glows as a thicker band. Outside it, a hydrogen-burning shell glows as a broad dimmer band. Deeper still, later stages can appear as thinner rings. The scene stays restful because it is imagined with slow light. A single number can hold the timescale without strain. Helium burning in a massive star can last about 1 million years, like a long era compared to a short season. This number anchors a scale shift. Surface patterns change over months and years. Interior burning stages change over hundreds of thousands of years. The star can look stable while its core quietly reorganizes. The second payoff lands with this contrast. The calm red surface does not reveal how quickly the interior is moving through its remaining fuels. As the star advances later burning, stages can be much shorter. Carbon, neon, oxygen, and silicon burning proceed in deeper shells. They require higher temperatures and produce heavier nuclei. The third visual anchor shows the deepening. The inner shells look thinner and brighter. The outer shells look thicker and dimmer. This is a physical hint. The inner stages release energy, but also lose energy rapidly through neutrinos. Neutrinos carry energy away with little interaction. They let the core cool even while reactions run. A short definition stays within one breath. Neutrinos are particles that escape dense matter with little absorption. The third payoff is immediate. When energy escapes efficiently, the core must run faster to maintain pressure support. This compresses the timetable of late stages. It also makes the interior more layered and more dynamic near the end. Another physical detail grounds the layered picture. Each shell can host convection. Rising and sinking gas moves heat and ash within that shell. Boundaries between shells resist mixing because composition changes density. A denser ash-rich layer tends to sit below a lighter fuel-rich layer. This creates stratification. Stratification is stable layering due to density differences. The definition stays brief. Stratification means layers persist because heavier material stays below lighter material. The fourth visual anchor shows the stability. The shell boundaries look like soft horizons in a deep ocean. Gentle currents churn within a layer. The horizon remains mostly intact. The fourth payoff lands in that horizon. Layering keeps fuels separated. It prevents the whole interior from blending into one uniform mixture. This separation is what allows distinct burning stages to coexist. A hydrogen shell can continue while helium burns deeper. Helium shells can continue while deeper fuels ignite. The limit of intuition enters softly and precisely. No direct view reaches these shells. All interior structure is inferred from models and from observed surface properties. Surface temperature, luminosity, and composition provide constraints. Yet many different interior configurations can produce similar surface outputs. Convection is especially uncertain. Mixing length models approximate it. Real turbulence is complex. This creates a limit set by indirect inference and by incomplete modelling of turbulent transport. Another limit follows. Rotation and magnetic fields can alter mixing. Their internal profiles are hard to measure. This adds uncertainty to exact shell thickness and timing. The fifth visual anchor makes the limit tangible. The cross-section looks clear in imagination, yet it remains a soft sketch. The shell boundaries shimmer slightly as if drawn in mist. The centre remains bright, but its exact size is not fixed. The fifth payoff settles calmly. Even with uncertainty, the layered principle remains robust. Different fuels ignite at different temperatures. This naturally builds nested shells. It naturally shortens late-stage timescales. It naturally prepares the core for a final transition. A final scale shift widens the view to the galaxy. The elements produced in these shells are not confined forever. Winds and later events distribute them outward. The layered interior becomes future chemistry for interstellar gas and dust. The closing visual anchor returns to the red surface. Beneath it, the nested shells glow silently. The surface remains calm while the core moves through its stages. The transition stays gentle and forward. Section 10 follows the star's remaining time in a quiet way. It compares the long life of early stages with the brief tempo of the final ones without rushing toward an ending. Time inside a massive star runs on more than one clock. The remaining lifetime shortens because late burning stages proceed faster as the core becomes harder to support. The primary visual anchor is a slow hourglass made of glowing layers. The upper bulb is wide and dim red like the extended envelope. The narrow neck is the region of shells. The lower bulb is the compact core, bright and small. The sand is not grains. It is imagined energy flow and fuel consumption. The first unlock arrives calmly. Early stages last long because fusion is efficient and the core is well supported. Late stages shorten because energy escapes easily, and the core must react faster to maintain pressure. A physical detail holds the interior scene. The shells are nested and uneven. The outer shells are thick and calm. The inner shells are thin and intense. Their boundaries are gradients. Within each shell, convection can stir material. Between shells, composition differences resist mixing. The first payoff lands within that resistance. Shells keep separate fuels available. This allows the star to keep shining even as the core changes. Yet the separation also means each stage has a limited reservoir. When one fuel is used in the center, the star moves on rather than refilling it. The second visual anchor widens to the surface. The red disk looks stable. Limb darkening stays in place. A faint halo surrounds the rim. Small surface brightness changes drift from convection. A slow pulsation swell shifts the overall light. None of these surface signs announce the interior timetable. The second unlock follows. The surface is a calm mask. Deep inside the core's pressure, balance adjusts continuously. When one core fuel is exhausted, the center contracts. Contraction heats the core, heating opens the next fusion channel. The star steps forward in its internal sequence. The primary analogy remains unique and natural. The interior timetable resembles a river that narrows into rapids. Upstream water flows broad and slow. Downstream the channel tightens, flow speeds up. The same total water continues, yet the pace changes with geometry. The analogy fits the hourglass. The wide upper bulb is slow time, The narrow neck is fast time. A third visual anchor returns to the shells with this narrowing in mind. The helium-burning region glows as a thick band. Deeper regions glow as thinner bands. Their brightness is higher, their volume is smaller. The third unlock arrives as a quiet reason. Late stages can lose energy strongly through neutrinos. Neutrinos escape from dense matter with little interaction. When they carry energy away, the core cools quickly. The core responds by contracting and heating again. This maintains fusion but accelerates it. The second payoff lands immediately. The star does not rush because it has intention. It accelerates because energy leaves more easily as the core becomes denser and hotter. A single number can anchor the scale without strain. The full life of a massive star can be about 10 million years, like a long era compared to a day. Within that span, the final deep stages occupy only a small fraction. The scale shift is gentle. Surface changes happen on years. The star's overall lifespan's millions of years. The final interior sprint can occur in far less than the full lifetime. The fourth visual anchor shows the scale shift as a calm gradient. The hourglass upper bulb glows for a long time with little change. The neck brightens more and more. The lower bulb becomes more compact. The pace feels different near the centre. The third payoff settles in the neck. As the timetable shortens, the star builds more structure. Shells stack closer together. Temperature gradients steepen. Density gradients steepen. A small change in radius inside the core corresponds to a large change in pressure. This makes the inner zones sensitive. It also makes convection and mixing more influential. The next unlock remains grounded. The surface can still look like a slow ember. It can still drive a wind. It can still form dust shells. These outward processes continue even as the core evolves. The star's appearance is shaped by the envelope's physics. The star's fate is shaped by the core's physics. Both proceed on different clocks. The limit of observation enters softly and precisely. No direct view reveals the core's current fuel stage. The stage is inferred from models that match surface temperature and luminosity. Those models depend on uncertain mixing and mass loss. If mass loss removes more envelope, then assume the core may be exposed earlier. If mixing is stronger, then assumed fuel can be distributed differently. This creates a limit set by indirect inference and by uncertain internal transport. Another limit follows. Variability and dust can bias luminosity estimates. Luminosity is a key input to evolutionary models. If luminosity is uncertain, the estimated remaining time is uncertain. The fifth visual anchor makes that uncertainty tangible. The hourglass is drawn in faint light. Its edges are blurred like chalk in fog. The neck width is not known exactly. The glow intensity shifts slightly with assumptions, yet the overall direction is stable. The upper bulb is long time. The neck is shortening time. The sixth visual anchor returns to the red star in the Milky Way. Dark lanes frame it. Dust shells surround it as faint arcs. The star remains a steady point of garnet light. The fourth payoff settles into that steadiness. Even with uncertain details, a red supergiant is understood as late in its life. It is a stage that does not last as long as earlier main sequence burning. It is an outward sign of inward evolution. The star's remaining time is not measured in billions of years. It is measured in far shorter spans on a cosmic calendar. The closing transition stays gentle and forward. Section 11 steps outward again. It places Mu Cephei within the Milky Way's structured lanes of gas and dust, showing how environment shapes what can be seen. The Milky Way does not form a smooth backdrop behind Mu Cephei. In that region, the star is seen through layered gas and dust that sculpt what light can reveal. The primary visual anchor is a slow drift along a spiral lane. A dim river of stars stretches across darkness. Dark rifts cut through it in long, soft bands. The rifts have feathered edges. They look like shadows laid over a faint glow. Mu Cephei sits near the outer weave of this lane. Its garnet point appears between two darker streaks. The first unlock is calm and direct. The environment around the star changes the path of light before it reaches open space. Dust and gas do not only add scenery, they filter and scatter, and they decide which parts of the galaxy remain visible. A physical detail holds the scene steady. The dark rifts are not empty gaps. They are denser regions where dust blocks more light. Their edges show gradients from nearly black cores to translucent margins. In the translucent margins, background stars are dimmer, but still present. This reveals that extinction increases with depth through the lane. Extinction means dust removes light by absorption and scattering. The definition remains brief. Extinction means dust dims and reddens light passing through it. The first payoff arrives inside this dimming. A star can appear deeper redded not only because its surface is cool, but because its light crosses dusty layers. The second visual anchor moves closer to the star's neighbourhood. The local field is crowded with faint points. Some are sharp, some are blurred by haze. A thin glow lies along the galactic plane like a soft band. Mu Cephei's own dust shell adds a faint blush around its point of light. This places two filters in the same view. One filter is the star's circumstellar dust, the other is interstellar dust along the line of sight. The second unlock follows gently. Two different dust layers can produce similar colour shifts. One acts near the star in arcs and clumps, the other acts across long distances in lanes and sheets. Their combined effect can make brightness and colour hard to separate into causes. A second payoff lands immediately. The galaxy's structure becomes part of the measurement, not merely a background. A single number can anchor the scale without strain. The Milky Way is about 100,000 light-years across. Light would need about 100,000 years to cross that span. This number supports a smooth scale shift. Mu Cephei is a point within a vast disk. The disk itself is a layered medium. It contains hot thin gas, cool dense gas, and dust mixed through both. The third visual anchor widens to a top-down view in imagination. The galaxy becomes a dim pinwheel. Spiral lanes curve outward. The outermost lanes look frayed. Their brightness is weaker. Their dust rifts are less continuous. Mu Cephei sits on a faint outer filament. The primary analogy settles in as a gentle image. The outer disk resembles the frayed hem of woven cloth, threads thin and separate near the edge. The fabric still holds together, yet its boundary is not sharp. This helps explain why edge of the Milky Way is a soft idea. The third payoff arrives within the frayed hem. Stars can exist far out, yet gas and dust become patchier. Light can travel through clearer corridors and through darker knots. The same type of star can look different depending on which corridor it occupies. The fourth visual anchor returns to the dark rifts. Each rift has a mottled interior. Within it, small transparent holes appear as tiny windows. These windows are not stable. Their shapes change across the lane. The fourth payoff follows. The interstellar medium is structured on many scales. Large lanes set broad extinction. Smaller clumps add local variation. Even if average dust is corrected, small clumps can still bias colour and brightness. Another physical detail anchors the medium. Where dust is denser, starlight is softer and redder. Where dust is thinner, starlight is whiter and more direct. This is a gradient across the sky. It is not a uniform veil. The fifth visual anchor shifts to a view along the line of sight. Multiple faint sheets overlap. Some sheets are thin and wide, others are compact and dark. Between them, gaps allow light to pass with less scattering. At this distance, light behaves as a traveller through layered fog banks. Some rays pass cleanly, some are redirected, some are absorbed and never arrive. The limit of observation enters softly and precisely. The true three-dimensional arrangement of dust is hard to recover from a two-dimensional sky view. Different clouds can overlap in projection. A dimming feature may sit near the star or far in front of it. Without precise distance markers for each dust layer, the path length through dust remains uncertain. This creates a limit set by line of sight confusion. Another limit follows from resolution. Fine structure in dust is smaller than the star's apparent size in the sky. Even when the star's halo is measured, the surrounding dust background can blend into it. This can bias estimates of the halo's brightness and extent. The sixth payoff arrives without urgency. Uncertainty in environment does not erase the galaxy's role, it clarifies it. Mu Cephei is embedded in a medium that sculpts its appearance. The star's cool surface sets a baseline red. Molecular absorption in its atmosphere deepens some bands. Dust near and far adds further reddening and dimming. The environment also sets the context for mass loss. The outflowing gas meets an interstellar background of varying density. In denser regions, the outflow slows and compresses. In thinner regions, it expands more freely. This can introduce asymmetry without any sharp event. The final visual anchor holds this interaction in quiet motion. A faint circumstellar shell expands into a background of uneven dust. One side meets a darker lane, the other side meets a clearer gap. The shell looks slightly brighter on the clearer side. The closing payoff settles gently. The Milky Way is not a silent stage. It is a textured medium that shapes what light can say. The transition stays soft and forward. Section 12 follows the star's outer layers in detail. It shows how uneven outflow and uneven surroundings create a halo that is lopsided and clumpy rather than perfectly round. The space around Mu Cephei is not symmetric even when the star itself feels round. The halo becomes lopsided because the outflow is clumpy and the surrounding medium is uneven. The primary visual anchor is a wide, faint envelope with one bright shoulder. The star sits near the centre as a red ember. On one side, the halo extends farther and glows slightly stronger. On the opposite side, it fades sooner and looks thinner. The boundary is a gradient everywhere, yet the gradients differ in slope. This is a concrete physical detail. The brighter side shows a slow fall off. The dimmer side falls off quickly. The first unlock arrives calmly. Asymmetry does not require a jet or a sharp event. It can arise from gentle differences in density and direction. A clump launched from a hotter surface patch can carry more mass outward. A shell lifted during a pulsation crest can become denser in one sector. The interstellar background can also resist the flow more on one side. The second visual anchor moves closer to the bright shoulder. The halo there is textured. Knots appear as dim beads. Between beads, faint filaments connect like wisps of smoke. Some filaments curve, some break into fragments. The second unlock follows from that texture. A clumpy outflow creates a porous envelope. Light can pass through gaps. Light can be scattered by clumps. The envelope becomes a mix of transparency and shadow. Shadow is a physical detail here. A denser knot blocks and redirects light. Behind it, a dim lane forms. The lane is soft-edged because scattering fills it partially. The first payoff lands inside the lane. The presence of shadow proves that the halo has structure in 3 dimensions. It is not a flat glow. It has depth, density, and uneven opacity. A simple term helps once and then steps aside. Column density means how much material lies along a line of sight. The definition stays short. Column density means the total material along a sightline through the gas. The idea is plain. Where column density is higher, more light is absorbed and scattered. Where it is lower, light escapes more cleanly. The primary analogy remains unique and natural. The envelope behaves like drifting steam over a cold lake. Steam is thick in some patches and thin in others. Wind pushes it into arcs, clear windows open and close. The lake surface is not seen directly, only the moving veil is seen. The third visual anchor widens outward to include the galactic background. A darker dust lane lies to one side. The halo's dimmer side points toward that lane. The brighter side points toward a clearer gap. This sets a gentle environmental gradient. The second payoff becomes immediate. External density can shape the halo. Where the interstellar medium is denser, the outflow slows and compresses. Compression can raise density and help dust survive, yet it can also increase extinction along that direction. Where the medium is thinner, the outflow expands more freely and remains more transparent. Both effects can produce a bright shoulder depending on viewing angle and scattering. A single number can anchor the scale without strain. Over 10,000 years, material moving outward at wind speeds can form a shell many light weeks across like a slow fog bank, spreading over a very long season. This number supports a scale shift. Surface changes happen in years. Halo shaping happens over many thousands of years. The halo is a long memory of many episodes combined. The fourth visual anchor shows memory as layering. Several arcs appear at different radii. They are incomplete. They overlap. The arcs are brighter on one side, they are fainter on the other. The third payoff arrives inside overlap. When multiple shells intersect, density increases where they cross. Those intersections can become bright knots in scattered light. They can also become darker knots in absorption depending on wavelength. This explains why the same region can look brighter at one colour and dimmer at another. Light behaves as a filter-dependent messenger. A signal would change character with wavelength because dust favours scattering of shorter wavelengths and transmission of longer ones. The limit of observation enters softly and precisely. The halo's three-dimensional shape is inferred from a two-dimensional projection. A bright shoulder could mean more material on that side. It could also mean better scattering geometry on that side. A dim side could mean less material. It could also mean more absorption along the path. Without full coverage across wavelengths and time, these causes can be hard to separate. This is a limit set by projection and by incomplete spectral information. Another limit follows. Clumps smaller than resolution blur into a smooth glow. Their true density contrast is hidden. Models must assume a clumping factor. Different assumptions can change inferred mass in the halo by large factors. The fifth visual anchor makes the limit tangible. The envelope is seen as a faint cloud. Its grainy knots shimmer at the edge of detectability. Some knots blend into one another. The eye cannot count them, yet the lopsided outline is clear. The fourth payoff settles gently. Asymmetry is therefore a robust qualitative feature even when details are uncertain. The halo is not a perfect sphere. It is a drift shaped by the local launch conditions and by the galactic environment. Another scale shift widens beyond the halo. The outflow leaves the star and eventually merges with the interstellar medium. It becomes part of the larger dust lanes. The star's personal envelope dissolves into the galaxy's shared fabric. The final visual anchor returns to the bright shoulder and then to the dim side. Both fade into the same darkness. The closing payoff remains calm. The lopsided halo is a quiet signature of mass loss interacting with a structured galaxy. It carries the record of slow winds and uneven surroundings. The transition stays soft and forward. Section 13 follows the chemistry carried by these winds. It describes how newly made elements move from deep shells to the surface and then outward into the surrounding medium. A red supergiant is not only a source of light, it is also a slow exporter of new chemistry into surrounding space. The early anchor is simple. Convection and mass loss move processed material outward, and the wind carries it into the nearby medium. The primary visual anchor is a calm view of the star's outer layers as a moving gradient. The disk glows deep red. Beneath the glow, broad convective patches drift like slow continents of brightness. At the edge, the limb darkens. Above the rim, a faint veil extends outward. Within that veil, clumps and arcs drift away. The first unlock arrives inside the drifting patches. Convection brings material from deeper layers upward. Convection is rising and sinking motion that transports heat and matter. The definition stays brief. Convection means hot material rises and cool material sinks in a circulating flow. The picture remains plain. A warm parcel rises, it expands and cools. A cooler parcel sinks. The flow repeats. Over time, this slow churning can mix the envelope. It can bring fusion products toward the surface. The first payoff lands gently. Surface composition can change even without any violent event. This explains why a star's spectrum can show signatures of processed in material while the surface remains calm. The second visual anchor shifts to the wind just above the photosphere. The outflow is not smooth. It contains denser knots and thinner gaps. Each knot is wrapped in a faint shadow because it scatters and absorbs more light. Behind it, a dim lane forms. The second unlock follows. Once enriched material reaches the outer layers, mass loss can remove it. The wind becomes a conveyor that transports atoms outward. The wind does not choose what it carries. It carries whatever the envelope holds at the time. The primary analogy remains unique and natural. The process resembles slow sediment being lifted from a riverbed and carried downstream. The river water is the outflow. The sediment is the processed elements. Some grains settle quickly in eddies. Some travel far. The river does not need a flood to move sediment. A steady current is enough over long time. The third visual anchor widens outward to the circumstellar shell. Arcs of dust and gas form incomplete rings. Their edges are soft. Their brightness is uneven. Within them clumps drift and spread. The third payoff arrives inside the arcs. These shells are not only structures of dust, they are containers of composition. Each shell can preserve the chemical state of the envelope at the time it formed. As shells overlap, the circumstellar region becomes layered in both density and chemistry. A single number can anchor the timescale without strain. Over 10,000 years, repeated outflow episodes can stack several shells like yearly rings that are blurred and incomplete. This number supports a scale shift. The mixing that lifts material can take years and decades in the envelope. The transport outward through the circumstellar region takes thousands and years. The merging into the wider interstellar medium can take longer still. The fourth visual anchor turns the scale into a quiet panorama. The star's personal envelope becomes a faint cloud. Beyond it, the Milky Way's dust lanes form broader dark gradients. The enriched cloud drifts into that larger fabric. The fourth payoff settles calmly. Material from a single star becomes part of the shared medium that later forms new stars and planets. The chain is slow. It is also steady across the galaxy. Another unlock arrives with a concrete physical detail. Chemistry leaves signatures in absorption bands. Molecules in the cool atmosphere imprint dips in the spectrum. Dust grains reshape the continuum and scatter light. The same star can show deeper bands when the atmosphere is cooler or when the line of sight crosses denser material. This means chemical diagnosis must account for physical structure. It is not only a matter of which elements exist, it is also a matter of where they sit in layered gas and dust. The fifth visual anchor focuses on a single clump moving outward. Its inner side is slightly warmer and brighter. Its outer side is cooler and darker. A gradient runs across it. The clump expands, its edges fray into wisps. The fifth payoff arrives with the gradient. Cooling and expansion allow molecules and dust to form more readily in the outer parts. This concentrates some chemistry in the colder regions. The wind therefore sorts material by temperature and density as it travels. The limit of observation enters softly and precisely. The detailed composition of the outflow is inferred from spectra, but spectra integrate along the line of sight. Different layers can overlap in projection. A clump can hide the region behind it. Dust can obscure deeper gas while adding scattered light. Models must disentangle these effects. Grain composition and size alter how extinction behaves. If grain properties are assumed incorrectly derived, abundances can shift. This is a limit set by degeneracy between dust and gas signatures and by unresolved clump structure. Another limit follows. The surface itself is variable. Convection changes local temperature. Pulsation shifts density. These changes alter molecular bands even if composition is constant. Time variability can mimic chemical change. Without long monitoring, a single spectrum can be misleading about steady composition. The sixth visual anchor returns to the star's rim. The halo glows faintly. The wind continues to drift outward. The sky behind shows a dark lane with feathered edges. The sixth payoff settles gently. Despite uncertainty, the broad direction is clear. A red supergiant enriches its surroundings through mixing and mass loss. The process is slow enough to be quiet. It is large enough to matter for the galaxy's chemical evolution. The closing transition stays soft and forward. Section 14 follows this enriched material farther outward. It shows how the circumstellar region blends into the interstellar medium, and how long-lived clouds carry a star's imprint across time. What leaves Mu Cephei does not stop at the edge of its faint halo. The outflow gradually blends into the interstellar medium, and the star's imprint becomes part of a larger cloud. The primary visual anchor is a slow dissolve of boundaries. A bright red point sits at the centre. Around it, the circumstellar shell looks like a dim, uneven ring of mist. Farther out, the ring breaks into filaments. The filaments drift into a background of darker lanes. The edge of the star's own envelope is not a sharp line. It is a fading gradient where identity slowly disappears. The first unlock arrives calmly. Mixing happens because the wind expands and thins. The surrounding medium has its own density and motion. Where they meet, the interface becomes a place of shear and compression. Shear is a difference in flow speed across a boundary. The definition stays brief. Shear means neighbouring flows slide past each other at different speeds. The physical detail is clear. At the interface, a smooth arc can become rippled. A once round shell can develop scalloped edges. Small curls form along the boundary. These curls grow into wisps. The first payoff lands inside the scallops. A star's envelope becomes textured not only by clumps launched from the surface, it is also shaped by how it rubs against its surroundings. The second visual anchor moves to one filament. It is narrow. It has a brighter spine and softer sides. Along the spine, knots appear like beads of denser material. Between knots, the filament thins into a translucent thread. Shadow plays a role here. Behind a knot, the background glow is slightly muted. This shows absorption and scattering from a localized density peak. The second unlock follows. The outflow carries dust and molecules outward. In the denser knots, cooling is stronger and dust survives longer. In thinner regions, grains can be rarer and more fragile. This sorts material by density. The primary analogy remains unique and natural. The process resembles ink stirred into water in slow motion. At first, ink is a concentrated plume, then it stretches into filaments. Edges curl into whirls. Over time, the plume becomes a faint tint everywhere. The water is the interstellar medium. The ink is the enriched wind. No sharp moment marks the change, only gradual dilution and mixing. The third visual anchor widens to a quiet map of nearby space. A faint cloud surrounds the star's direction. Dark lanes of dust frame it. Within the cloud, brighter and darker patches appear. Their edges are soft, their interiors are mottled. The cloud is not static. It has internal turbulence and slow drift. A small term helps and then steps aside. Turbulence is chaotic motion across many scales. The definition stays short. Turbulence means irregular swirling motion that mixes material on many sizes. The third payoff arrives inside the mottling. Turbulence can fold and stretch the enriched material. Folding increases contact area, stretching spreads it thin. Both processes speed mixing without any violent shock. A single number can anchor the scale without strain. A cloud region can persist for about 10 million years, like a long epoch compared to a brief season. This number supports a scale shift. The star's shells form over thousands of years. The cloud that absorbs them can live for millions. The chemistry is therefore stored and transported long after the star has changed. The fourth visual anchor brings attention to temperature gradients. Near the star, the outflow is warmer. Farther out, it cools and becomes more molecular. In the interstellar medium, some regions are cold and dense, others are warmer and thinner. The boundary between them is a gentle gradient rather than a wall. This gradient matters for dust. In colder, dense parts, grains can grow by collecting atoms. In warmer, thin parts, grains can be eroded or dispersed. The fourth payoff settles calmly. The environment acts as a filter that decides what parts of the star's export remain solid dust and what parts remain gas. This changes how the material participates in future clouds. Another unlock arrives through geometry. When the wind expands into a denser region, a bow-shaped compression can form. The front edge becomes brighter in scattered light because density rises. The trailing side becomes more diffuse. This makes a one-sided shape even if the original wind is nearly spherical. The physical detail is a curved front edge with a smooth, bright ridge and a softer wake behind it. The fifth visual anchor holds that ridge in stillness. The ridge is faint. It is not a dramatic arc. It is a slight enhancement that follows a curve. Along it, tiny ripples appear like shallow waves. The fifth payoff lands inside the ripples. Even gentle compression can organize dust into a coherent feature that persists for a long time. It becomes a marker of interaction between star and medium. The limit of observation enters softly and precisely. The true mixing state is difficult to measure directly. Emission and absorption lines integrate along the line of sight. Foreground and the background clouds can overlap in projection. A faint ridge can be confused with unrelated dust in the galactic lane. This is a limit set by projection and by uncertain three-dimensional placement. Another limit follows. Dust properties vary. Grain size and composition change how light is scattered and absorbed. If grain assumptions are wrong, the inferred mass of dust in the mixed region can shift. This makes exact budgets uncertain, even when the qualitative mixing picture is clear. The sixth visual anchor returns to the dissolve of boundaries. The circumstellar shell is still visible near the star. Farther out, it becomes only a slight tint in the interstellar medium. The star's unique halo becomes a shared haze. The sixth payoff settles gently. The star's influence is not only in light, it is in matter that quietly joins a larger cycle. The cloud that holds this matter can later cool and fragment. It can contribute material to new stars and their surrounding disks. The transition remains soft and forward. Section 15 resolves the journey without urgency. It returns to Mu Cephei as a steady red presence. It places the star within long galactic time and ends in a calm, stable view. Mu Cephei remains easiest to notice when attention rests on its colour, a steady garnet tone against a darker lane of the Milky Way. The quiet answer is already present. A cool supergiant glows red. A layered environment shapes that red into a deeper ember and carries its matter outward. The primary visual anchor is a wide still view of the star as a lone crimson point above a faint mottled dust band. The band has soft gradients. It has darker rifts with feathered edges. The star's halo is barely visible as a pale blush that fades unevenly. The first payoff arrives at once. The redness is not only a surface property, it is also a story written by molecules, dust and distance. The gaze moves closer in thought. The photosphere is not a hard shell. Its limb is a gradient where brightness falls off toward the edge. Above that edge, the atmosphere becomes cooler and more extended. In that cooler region, molecules imprint broad absorption. Dust can begin to survive in denser pockets farther out. The star remains stable as a point, yet its outer layers are structured. The second visual anchor is a slow sweep along the star's rim. The limb darkening is gentle. The edge looks softer than the centre. A faint haze lies just beyond the rim. It is not uniform. It has a few brighter wisps and a few dim gaps. The second payoff settles calmly. A single point of light can contain a layered geometry. Brightness does not fall off like a neat step. It falls off like mist thinning into night. One main number can anchor the scale without strain. Mu Cephei is about 3,000 light-years away, so its light travels about 3,000 yearly cycles before reaching this region. The comparison remains simple and safe. The travel time matches thousands of seasonal turns on a temperate world. This creates a gentle scale shift. A change near the star can be ancient by the time it becomes visible. Yet the star itself evolves over far longer spans. The sightline therefore carries both immediacy and deep time in the same beam. The third visual anchor widens to the circumstellar envelope. The halo is not a perfect circle. It is slightly extended on one side. It fades faster on the other. Within the halo, faint knots and wisps suggest clumps. Each clump casts a soft shadow lane behind it in scattered light. The third payoff appears inside that shadow. The halo is not only decoration, it is evidence that mass loss has shape. It has density contrasts. It has gaps where light escapes more freely. The primary analogy remains unique and natural. The envelope behaves like a tide entering a shallow bay. Water spreads outward in a broad sheet. Sandbars and channels guide the flow. Some regions deepen and hold more water. Some regions remain thin and reflective. Over time, the boundary between bay and open sea becomes hard to define. The bay is the circumstellar region. The open sea is the wider interstellar medium. The tide is the wind and its dust. The fourth visual anchor follows the tide outward. The shell becomes broken arcs. The arcs become filaments. The filaments blur into the background dust lane. At the far edge, identity dissolves into the shared haze of the galaxy. The fourth payoff lands gently. Material from one star becomes indistinguishable from the medium that surrounds many stars. The cycle is quiet. It is also continuous. A second concept helps and remains contained. Mixing is the gradual blending of flows and compositions into a common medium. The definition stays brief. Mixing means separate materials spread and blend until boundaries are no longer clear. The idea returns to plain language. Uneven density causes uneven blending. Shear at interfaces creates ripples. Ripples become curls. Curls become thin streaks. The structure grows finer as it spreads wider. A limit of intuition enters softly. It is difficult to imagine a boundary that fades rather than breaks. The mind expects edges. It expects surfaces. The interstellar medium is more like gradients and overlapping layers. The fifth visual anchor makes the gradient tangible. The dust lane in the background shows a dark core. It fades to a translucent margin. Within the margin, stars are dimmer, but still present. Within the core, stars nearly vanish. This shows extinction increasing with depth. The fifth payoff follows. The same light beam can be altered by both the star's own dust and the galaxy's dust. A redder colour can arise from the cool temperature. It can also arise from filtering along the path. Both causes can coexist. The limit of observation appears with precision. Spectra and images integrate along the line of sight. Different layers overlap in projection. A clump near the star can align with a cloud far in front. Dust properties can vary and grain size changes how scattering behaves. When grain assumptions shift, inferred mass and composition shift with them. Resolution also imposes a ceiling. Fine clumps, smaller than the resolving power, blend into smooth glow. This is a limit set by projection dust degeneracy and finite resolution. The sixth visual anchor returns to the star itself. The garnet point remains steady against the dust band. The halo is faint but present. The background is crowded with dim stars that fade into the lane's darker rifts. Light behaves as a messenger that carries both source and journey. A signal would always arrive after crossing layers that leave subtle fingerprints. The sixth payoff settles into calm closure. Mu Cephei stands as a vivid example of how a star's outer layers wind and environment become one linked system. The red glow is a surface temperature. It is also a path through dust. The halo is mass loss. It is also interaction and mixing. The galaxy is not a stage. It is the medium that receives and reshapes what leaves the star. The final scale shift rests without strain. A single star's episodes unfold on short spans compared to the galaxy's slow circulation. Yet those episodes still matter, because they add structure and material to the shared medium. The ending remains soft and stable. The view stays wide and still. The garnet point holds its place near the edge of a dark lane. The surrounding haze continues to thin outward until it is indistinguishable from the Milky Way's quiet texture.